Good day, everyone. This is the second video on the topic of hypothesis testing, which we started last video, where we talked through a variety of definitions. It was largely definition heavy and a bit light on the actual applying exam style questions and examples. Whereas here, now we've got the definitions and the boring stuff out of the way, we can go forward and apply some of this logic to some real life examples and exam style questions. So without further ado, here are the warm-ups. So 4 questions, questions 1 through to 4. If you've got a printout of this, if you can do, attempt the questions on the printout, then play the video once you've tried the questions. Or if you've not got a printer, if you could please just copy these down, pause the video, do your own worked answers, and then press play when you're ready to check your answers against my solutions. So without further ado, here's the solution to question 1. So question 1, we have a random variable, big X, which is binomially distributed with 30 trials, probability of success 0.2. First of all, we need to use the calculator to find the probability that this particular distribution takes a value of 4. And so what we need to do here is to get the classes calculator. So we get onto the binomial PD mode. Okay, so it's PD if we're trying to find a particular probability, not greater than or less than, but X is exactly equal to 4. To get onto binomial PD, I'll just talk you through how you get onto that. We press menu, option 7, and then option 4. You then go to variable mode, so press 2, and then type in the parameters. So X is the number of successes that we're interested in this case 4. N is the number of trials, which we're told is 30, and the probability of success is 0.2. And so press equals, and we'll get an answer to 3 significant figures of 0.133. And so that's our answer for question 1 part A. So we can just fill this in here. So we've got 0.133. For part B, we're wanting the probability that X is less than or equal to 4. Now, because we've got an inequality symbol for this one here, we need to use binomial CD. So for this one, we press menu, again option 7, but this time we scroll down on this screen to get binomial CD on the next screen. Then we press option 1. Again, the parameters are more or less the same, in fact exactly the same, but now what we're going to do is not work out the probability of big X equaling 4, but this is going to calculate for us the probability that big X is up to and including any value, including 4. So this is going to be the probability that big X equals 0 or 1 or 2 or 3 or 4. So press equals, we get to 3 significant figures, 0.255. So that's our solution for part B. So 0.255. For part C, we want to work out the probability that big X is less than 6. Now that's a slightly trick question. We need to reframe this in terms of less than or equal to. So less than 6 is the same as saying it's less than or equal to 5. And so we just press AC to go backwards, and then change the 4 to a 5. And then we get 0.428 to 3 sig figs. The last one, for probability that X is greater than 7. Again, we need to rewrite this. This is the same as saying it's 1, subtract the probability that X is equal to or less than 7. If we take away the probabilities of X being equal or less than 7, we're left necessarily then with a probability of X being 8, 9, 10, all the way up to 30. So what we need to do here is to press AC, go back and press X for being 7. We then get 0.761, and so we need to do 1 subtract 0.761. Not 0, sorry. So it's 1 subtract 0.761. So using your calculator or whatever, you should get 0.239. And so that's all of question 1 completed, each and every part. So moving on to warm-up question 2. We're told we've got a company that manufactures AA batteries, and apparently they have evidence to suggest that 2% of their batteries produced last less than 24 hours when used. A consumer watchdog would like to test whether the company's claim is true, write down 2 suitable hypotheses. So what I'd suggest we do is just go on the premise of innocent until proven guilty and assume by default that this company are telling the truth and that this company are correct. And so I just always assume that the company is correct to start with. Give the company the benefit of the doubt. So assume that company are correct in their claim. And so with that assumption, our null hypothesis, H0, would be that what they say is true. So that would be that P equals 0.02. In other words, that the probability of a battery lasting less than 24 hours is indeed just 2%. The alternate hypothesis, H1, which this watchdog is trying to show might be true, must be that actually a greater proportion of batteries than 2% fail before 24 hours. And so they are trying to show that the probability, the proportion of batteries produced lasting less than 24 hours might actually be greater than 2%. So H1, the alternate hypothesis, is that the probability is greater than 0.02. And then if you want to, you can maybe put in brackets where P is the probability of a battery lasting less than 24 hours. Now, question 3, we're going to use what we did in question 2. And so of a batch of these 100 AA batteries, 5 were found to last less than 24 hours. Suggest a suitable test statistic. Well, the test statistic is something which we're recording when we do the experiment. And so what I'd suggest here, the most obvious one is, it's just simply the number of batteries lasting less than 24 hours. That's the number of batteries lasting less than 24 hours. You could also have defined the test statistic as the proportion of batteries lasting less than 24 hours. So the next line, assuming the test statistic is binomially distributed and testing to a 5% significance level, we're going to find the critical region for this test. And so what we need to assume here is that X is binomially distributed. We're going to have 100 batteries, so essentially that's 100 trials, with a probability of a battery lasting less than 24 hours being 0.02. This is our assumption for the model. So we need to find the critical region for the test. What this is saying is it's the probability of us incorrectly saying that the null hypothesis is incorrect. So it's the probability of rejecting H0 by mistake. So find the critical region for this test. So what we need to do here is to find what actual number of batteries would cause us to reject H0, assuming this to be true. So there's a few ways of doing this. What I'd honestly suggest is just to do trial and error on the calculator. So we have here 100 trials. The chance of a battery failing, not success, is 0.02. And we want this number to be 0.95 or less. So we're looking for about 0.95. So let's try, for example, let's say 3 batteries failed. 0.85. So we're nowhere near with 3. So let's just take it up to 4. Now that's very close to 0.95. So let's just think about what we've just worked out here. So we just worked out the probability of up to 4 batteries failing. And we were told that's 0.949. So based on this, we can therefore deduce that the probability of a number of batteries failing is greater than 4, must be 1 minus this figure here, which is 0.051, which is very, very close to 5%. But ultimately, this figure here is greater than 5%, so that's not quite significant. That is still within our 95% limit. This isn't critical. But if we take it up one and think about the probability of a number of batteries lasting less than 24 hours being 5 or less. So if we go back here, press AC, and then X, set it to 5, we have for this one 0.985. Again, that's to 3 significant figures. We could give it to 4 decimal places if we wished, just to make sure we don't have any rounding error. So 0.9845. Now, as you can see, this is more than 0.95. So this tells us that the probability of a number of batteries lasting less than 24 hours being more than 5 is 1 minus this probability. And that gives us 0.0155, which is now critical. And so before I actually answer the question and say find the critical region for this test, it's worth just dwelling for a second on what this means. First of all, it does mean that the critical region is where X is greater than 5. So in fact, why not write this down? So the critical region is X greater than 5. Or if you wanted to, we could say X equal to or greater than 6. Now, in terms of thinking about this a bit further, the critical region is this, but we can now work out the actual significance level. So the actual significance level of this is the probability of incorrectly rejecting H0. Now, the question doesn't ask this, but we may as well just see if we can work this out. So the actual significance level is the probability of our test statistic falling within a region which would cause H0 to be rejected, and that would be if X was 6, 7, 8, 9, or so on. So it's this probability here. So the actual significance level would be 0.0155, which is about 1.55%. So the actual significance level is often different to the stated significance level. And of course, if you're wondering if H0 would be accepted or rejected, then we can go a bit further and say that H0 would still be accepted. Because what we had is we had 5 batteries that lasted less. And so here, for 5 batteries, that is just inside, by the skin of its teeth, the accepted region. So it's not quite critical, but it's so close to being critical it very almost is. But we'd still actually just accept it for X equals 5. If for one more battery, we would have rejected H0. Question 4, Calculus Corner. We've got a curve to differentiate, which is y equals x cubed minus the cube root of x all over 3. So what I'm going to suggest first of all is we rewrite this in power form and say it's the same as 1/3 x cubed minus 1/3 x to the power 1/3, because the cube root of x is the same as x to the power 1/3. So we can now differentiate this by finding dy by dx. So we take the power of x, bring it to the front, and drop the power down by 1. And so x cubed, the 3 comes to the front and multiplies the coefficient. So 1/3 multiplied by 3 is just 1, and x cubed now becomes x squared. In the similar way with the second term, the 1/3 power comes to the front and multiplies the 1/3 in front of the x. 1/3 multiplied by 1/3 is obviously 1/9. And we subtract 1 from the original power of x. So 1/3 minus 1 becomes minus 2/3. And this is therefore the gradient function dy by dx for this particular curve. Okay, so let's go on and have a look at the main part of the lesson. So, getting straight into it, no messing around, just let's find some critical regions for one-tailed test. So a one-tailed test is just a test of a type where our null hypothesis is a probability is equal to something, and the alternate hypothesis is where the probability is either greater than what we state for H0 or less than. So it's just going one way or the other. But the easiest way to understand this is by just doing some examples, hence this one here. Anyway, so we've got that a single observation is taken from a distribution with 6 trials and P being the probability of a success. We've given what H0 is and what H1 is. For part A, we're told to use a 5% level of significance to find the critical region. So let's just be setting this up on our ClassWiz calculators. So what we need to do is to type in our parameters correctly. So menu 7, almost always it's going to be binomial CD. Press 2 for variable, and number of trials is 6. Assume H0 to be true, so P is 0.35. So we always start by assuming H0 to be correct. And if we assume H0 to be correct, then we're assuming that the distribution is binomial with 6 trials with probability of success 0.35. So again, best way to start these off is by trial and error. We're hunting for a value of roughly 0.95 because of this 5% significance level. So first of all, let's have a look and try, say, I don't know, x being equal to 3, just plucking that out from nowhere. That's 0.882, so that's not going to be critical, but it's a starting point. So I could write down, first of all, the probability of x being greater than 3, say. That's obviously 1 minus the probability of x being up to and including 3, which is 1 minus the figure we just had, which just give it to 4 sig figs, just to avoid any rounding error. That's 1 minus 0.8826. Which gives us 0.1174. And like I said earlier, that's not going to be significant. This is about 12%, which is greater than 0.05. Hence, that's not significant yet. So next, try probability of x being greater than 4. That's obviously 1 minus the probability of x being up to and including 4. So we need to just toggle back on our ClassWiz and work out this. We set x equal to 4. So press AC, x being equal to 4. So it's 0.9777. So 1 minus 0.9777, and that gives us 0.0223, which clearly is less than 0.05. So this is the first value to become in the critical region. And so the critical value is x equal to 5, the first value where x is greater than 4, in other words. So our critical region is where x is greater than 4, and if you think about the number of trials, there's only 6, so we could just say the critical region is where x equals 5 or 6. Now we can think about part B, the actual significance level for this test. Well, the actual significance level just to recap from last lesson, the actual significance level is one and the same thing as a probability of incorrectly rejecting H0, incorrectly rejecting the null hypothesis. So it's the chance of landing in this critical region, assuming this to be true, and if this were true. Of course, anything can happen, so what's the small, albeit possible, chance of landing in the critical region and therefore rejecting H0 if this were true? And it's this figure here. It's a probability of getting either x being 5 or 6, which we worked out was this figure here. So it's 0.0223 as a decimal. So because we're given a percentage for the level of significance, we may as well keep it consistent rather and do the same for the actual significance level. So 0.0223 is to 3 sig figs 2.23%. So like I said earlier, the actual level of significance is often different to the nominal level of significance. Worked example 2, there's 4 in total, so this is worked example number 2. A company distributes sunflower seeds in packets of 50, and on average 30 of these seeds will germinate. A gardener believes that pre-soaking the seeds in water before planting will increase the number that will germinate. He might be onto something here, or maybe he's deluded. We'll see. So part A, describe the test statistic and state suitable null and alternative hypotheses. So let's have a think. So what we need to do, I would say, is to give the company or the manufacturer of these seeds the benefit of the doubt first. This gardener could be a bit of a raving lunatic. We don't know, do we? So for part A, the test statistic, there's a few you could mention, well, 2 I'd say. The first obvious test statistic would be the proportion of seeds that germinate. What I'd suggest though, because it's actually an experiment, we can use 50 and count the number of seeds that germinate. I'd just say the easiest test statistic to use, I'm struggling to say statistic today, I don't know what that is, but there you go, no one's perfect. So the test statistic, I would say the best one to use would be just simply the number of seeds that germinate. Number of seeds that germinate. And also now we need to state suitable null and alternate hypotheses. So what I'd say is just state first of all what you want P to represent. So we're going to say let P be the proportion of seeds that germinate. Okay. Then what we can say is that H0, the null hypothesis, is what you'd assume to be true, that the proportion of seeds germinating, well, in a pack of 50, it says on average 30 will germinate. So 30 out of 50 as a proportion is 0.6. The alternative hypothesis, H1, would be that the proportion is greater. This gardener, he or she, is actually thinking that they can increase this proportion. So the alternative hypothesis is going with this gardener's feeling here, that actually they could increase the proportion above 0.6. Part B, we're going to use a 10% level of significance to find the critical region for a test to check whether this belief may be true. So they come in packets of 50, so 50 seeds is enough to give us a good sample size. And again, we're looking for a 10% significance level. So by trial and error, we're going to hunt for a number which gives us a probability of around the 0.90 mark. So again, I'd just say trial and error, make sure you're on binomial CD. Let's, for example, try 30. 30 is what you'd expect, 30 out of 50. Proportion but germinate is 0.6. As you can see, nowhere near critical, because 30 out of 50 is what you'd expect. So let's just edge this number up. You can do it very quickly on a calculator. 66%, still nowhere near. 32, nope. 76%. 33, getting closer now, look. So let's try and take this up one. Let's try 34. 34, okay. So what I'd do here, I'd write down 34. In fact, 34's gone above, hasn't it? So what I'd suggest maybe is actually go back to 33. I'd always do one either side. One below the level of significance, one above, just so you can get a clear picture in your head about if you're doing it correctly or not. So as you can see here, 33. So the probability that 33 or less would germinate is this figure here. That's 0.8439. .8439. So therefore the probability of more than 34 germinating, or actually 34 itself, that would be the same as 1 minus the probability of x being 33 or less. In fact, we can put in this figure now. And that gives us 0.1561. And that's greater than 10%, so that's not yet critical. If we go up one though and try probability of x being 34 or less, so go back and press in 34 for x, we get 0.9045. Therefore, the probability of 35 or more seeds germinating will be 1 minus 0.9045, which is 0.0955. And this is now less than 10%. So this has now become critical. And so 35 must be our critical value. It's the first value which would push the probability below 10%. So that tells us what the critical region is. So therefore, the critical region is anything above 35, including 35 itself. So 35 inclusive, all the way up to every single seed germinating in the pack. If we had 34, 33 or 32, we'd be thinking, well, that's more than what we'd expect, but that's not beyond the realms of possibility. 35 or more, we'd start thinking, well, okay, we need to reject H0. It's looking like this gardener might be onto something. Part C, state the probability of incorrectly rejecting the null hypothesis using this critical region. So, now for part C, probability of incorrectly rejecting H0 just to recap from earlier, that's the same as the probability of landing in the actual significance level. The actual significance level for this test is 0.0955, which as a percentage, damn, I forgot the zero, sorry, 0.0. 955. So we're talking about 9.55%. So the chance of incorrectly rejecting H0 is a chance of H0 being true, yet it was rejecting it wrongly. That's 0.0955. So about a 10% chance, which actually, on the grand scheme of things, is relatively high. Work example 3, we're now going to talk about two-tailed tests. Okay, two-tailed tests are where we have an alternative hypothesis where the probability is simply not equal to the probability we have for H0. So this could be either on the higher side or the lower side. So the lower side is the lower tail, the higher side we call the upper tail. So first of all, we need to use a 2% level of significance to find the critical region for this test. Now, an important point here, the significance level tells us the total significance level for both tails inclusive. And so what we need to do here, because we have a 2% level of significance, we need to aim for 1% or as close to 1% in each tail. So what we want to here is that the probability in each tail must be as close as possible to 0.01. And again, as ever, we assume the H0 to be true. So we're going to be assuming for here that X is binomially distributed with 40 trials, and assuming H0 to be true, P is 0.25. So let's take each tail in turn. So first of all, let's have a think about the lower tail. So for lower tail, we want that to be as close as possible to 0.01. We'll never get it exactly 0.01, but it's exceptionally rare, so it's as close as we can. So let's use a class whiz and type in our parameters correctly. So we've got 40 trials. Probability of success is 0.25. So we're wanting it close to 1%. So let's go really low. Let's just try 0. Incredibly low, too low. 10 to the minus 5, no, that's too low. Try 1. 10 to the minus 4, still freakishly low. Try 2. 10 to the minus 3, so that's 0.001. So still on the low side. Let's try going higher slightly. Whoops. Try 3. Okay, this might be worth recording. And so the probability of having up to and including 3 successes, that was about 4695, so about 0.0046. Let's just call it 0.00470 actually. To 3 significant figures. In fact, no, I'll change my mind. Let's give it to 4 significant figures because that just eliminates any chance of having any rounding error. So that's going to be 0.004696. 4696. Whereas the probability of X being up to and including 4, hopefully this will be closer to 0.01, but we can find out. So let's try X being 4. Well, that's now over 0.01. So we get 0.01604. So, which is closer? So a bit of mental arithmetic, or you can check on your calculator, do 0.01 subtract each of these and see which is the one which is closer to 0. Well, this is about 0.0054 away, whereas this one here is 0.00604 away. So actually this one is closer. And so for our lower tail, we're going to take x up to and including 3, because this is one that gives us a tail close to 0.01. So what we say here is, because the probability of x being less than or equal to 3 is close to 0.01, we're using that for our lower tail. So the lower tail is x less than or equal to 3. So now we need to apply the same idea to the upper tail. Again, if you're not sure where to begin, use some trial and error. You can do it incredibly quick with a calculator. There's nothing to lose. You can always just go back if you get a value which is too high. It's very easy to do. So the upper tail, we're wanting a value close as possible to 0.01 yet again. So let's, for example, try, I don't know, 15. 0.97. We're wanting something close to 0.99. So try 16. 0.9884. So that's looking pretty good. Okay, so here, that's up to and including 16. So the probability of x being 17 or greater, that's 1 minus the probability we just worked out, the probability of x being up to and including 16. So just to refresh our memories, what we had here was 0.9884. So 1 minus 0.9884, that gives us 0.0116. That's very close to 0.01. But let's just try going 1 higher, just in case. The chance of x being 18 or greater, that's 1 minus the probability of x being up to and including 17. So again, with a calculator, press AC, change a 16 to a 17, we get 0.9953. So 1 minus 0.9953, we get 0.00465, which is obviously not as close. The closest one to giving us a tail of 0.01 is this one here. So therefore, the upper tail we can take to be x being 17 or greater. So therefore, the critical region, that's a combination of two critical regions actually. The critical regions are at the lower end, x less than or equal to 3, and also coupled with that at the upper tail, x being greater than or equal to 17, all the way up to anything as high as it can possibly go. So there was 40 trials, so it's all the way up to and including 40. For part B, the actual significance level of the test is the actual significances of both tails. And so for this one, the actual significance level, well, for the lower tail, we chose x being 3 or less. That had a critical significance level of 0.004696. Whereas the upper tail, what we chose was this probability here. So we're going to add these two together. So part B, the actual significance level is going to be 0.004696 plus 0.0116. I could have given this to an extra significant figure, in fairness. Maybe slightly naughty if I didn't. Anyway, when we add these two together, we get 0.0163, two three sig figs at least, which as a percentage, we get 1.63%. So that's for total significances by thinking of both tails together, which is what we need to do. Final one, worked example 4, we have a restaurant owner noticing that 1/8 of his customers order seafood risotto from the menu. He decides to change the recipe and believes that this will change the proportion of his customers who order it. So first of all, we need to suggest a model and state suitable null and alternative hypotheses. So just to give myself a bit more space here, I'm going to just divide the screen up. The writing got a bit scriddly, if that's even a word, which it's not. It got a bit smaller for the last example. So suggest a model and state suitable null and alternative hypotheses. So we've got to assume the restaurant owner can do some maths and that he can work out what 1/8 is. And so the model we're going to assume here, going to model it as binomial. Remember, all hypothesis tests for year 12 will be binomial. So model as binomial, n being the number of trials, p being the probability or proportion of customers that actually order the risotto. And so H0, we're going to assume that this restaurant owner is correct and that to start off with 1/8 of his customers ordered seafood risotto. So 1/8 as a decimal is 0.125. The alternative hypothesis is that when he changes the recipe, this proportion of customers ordering it will change in some way. So either the customers will like it and this proportion will increase, or the customers will be put off and not as many will order it again, and so in that case the proportion may be lower. So this is a two-tailed test. He's just saying the proportion may change one way or the other. So H1 is that the probability is not going to be equal to 0.125 after this change. So for part B, he takes a random sample of 30 customers. We need to find at the 5% level of significance the critical region for this test. And so, assuming H0 to be correct, the number of customers is 30, and 0.125 level of, proportion of customers liking it or ordering it. So we need each tail to be as close to 2.5% as possible because it's half of the 5%. So I need each tail as close to 2.5% as possible. Again, we need to start by looking at the lower tail. So we know that we've got 30 trials, or 30 customers, each one can be considered a trial. The probability of a particular customer choosing the risotto based on previous experience is 1/8. So we need to put these parameters in. So AC, or to go to binomial CD for correct function from scratch, menu, option 7, scroll down to binomial CD, option 1, and then variable. So here what we need to do is type in the number of customers is 30, and the probability of a customer choosing this dish is 0.125. We start with a lower tail, and so let's try 0 customers. The probability that 0 customers out of 30 choose the risotto. We get 0.0182, so let's record that first of all. So for the lower tail, we get the probability of x taking the value of 0 is 0.0182. In fact, going to an extra significant figure, 0.01821. Whereas the probability of x being up to and including 1, basically 1 or 0, let's see how that compares. Remember, we want up to about 2.5%, or as close to 2.5% in each tail as we can. So that's about 1.8%. Let's try the value 1. That's 0.09. That's ballooned to about almost 10%. So clearly, it doesn't take a genius to see that the value which gives the tail as nearest to 2.5% is x being up to and including 0, just x equals 0. So the lower tail must be x equal to 0. So just write that down. The lower tail for critical region for the lower end is x equal to 0. Now let's just try the upper tail. So again, we can use a trial and error approach. So let's try, I don't know, maybe 10. That's far too high. 10's far too high, isn't it? So maybe, I don't know, 6. That's not near to 2.5% yet. We're looking for about 0.975. That'd leave us with 2.5% when we take 1 away from it. So let's try 7. 7's quite close, and so probability of x being 8 or greater is 1 minus the probability we just worked out, which was up to and including 7. So what we had there, let's move this calculator to the side, is 1 minus 0.972. In fact, go slightly more, 0.9725. 725, yeah, to 4 sig figs. And that gives us 0.0275. Let's compare this with the next one up, see if it's closer to 2.5%. That's pretty close to 0.025, so probably not, but let's try it. The probability of x being 9 or greater, that's 1 minus the probability of x being up to and including 8. So the class whiz, toggle back with AC, type x as 8. The chance of the statistic taking a value of up to and including 8 is 0.9909, and so rounded off that would be 0.9910. So 1 minus 0.9910, that gives us 0.0090. So it's not too hard to see that the value which will give us a tail nearest to the required 2.5% is this tail here. So therefore that's our upper tail. So we've got the lower tail from before, which was x equal to 0. Now we know the upper tail is simply x being 8 or greater, all the way up to the maximum, which is obviously 30 out of 30. So putting these two together, critical region is going to be at the lower tail, x equal to 0, and at the upper end, this region where x is between 8 and 30 inclusive. So, for part C, state the probability of incorrectly rejecting H0. That's the same as working out what the actual significance level is. So probability of incorrectly rejecting H0. That's the same as the actual significance level. So the chance of incorrectly rejecting H0 is, like I said before, essentially this idea. It's the idea that H0 is actually the correct model, but just by some unlucky chance, we end up falling in one of these narrow regions, either the very extreme bottom end or the very extreme top end. Yet H0 being correct, yet because it just happens to fall into these two, we reject it for the wrong reasons. Not actual significance, I mean actual significance level, sorry. Must be very tired today. And so all we need to do here is just to add up the actual significance level of the two tails. So the first tail, x equal to 0, is this value here, and the upper tail is this probability here, 0.0275. And so if we add these together, what we're going to get is 0.01821 plus 0.0275, which will give us three significant figures, 0.0457, which if you want it as a decimal would be, sorry, if you want it as a percentage, which you don't need to. The probability is probably best left as a decimal here, which is fine. Or if you wanted to, you could give it as a percentage. There's no particular harm in doing so, but you just don't need to do this. So the actual probability of incorrectly rejecting H0 is about a 4.5% chance, 0.0457. So hopefully you found those 4 examples useful. Maybe took a bit of time, but I'd rather spend too much time than rushing through and leaving you with a greater chance of being confused. So as ever, it's over to you now. So I'd like you to go to page 103 and 104, exercise 7b in the statistics and mechanics book. This will give you plenty of opportunity to practice these skills and get your head around them. Try every single question from this exercise. As ever, email me if you're unsure or get yourself stuck, or leave a comment in the comment section and I'll get back to you as soon as I can. If I don't respond in the comment section or an email straight away, do feel free to send me a reminder. Sometimes I get sidetracked and forget. As ever, thank you very, very much for listening. I do appreciate it, and you'll hear from me soon in the next video. Ciao for now.